Our last speaker in this session is Yue Niu, telling us about cost-sensitive computational adequacy of higher-order recursion in synthetic domain theory. So, please go ahead.
Great, thank you. So let me first acknowledge our sponsors and thank them for supporting this work. So the story for this talk begins with a type theory called CAF that we've developed to unify both cost-sensitive and functional programming verification. And what I mean by functional is the pure I/O behavior of programs or data structure invariance. And what I mean by cost-sensitive is the computational cost or resource usage of programs. In other words, functional properties are about if a program is correct, and cost-sensitive properties are about how much resource a program uses during computation. Now, this type theory CAF supports a denotational style of cost analysis. The connection to operational cost semantics is made via a cost-sensitive generalization of computational adequacy of Plotkin. In prior work, we instantiated this property for a language equipped with first-order recursion. The goal of this talk is to extend this result to account for higher-order recursion. So the outline of the talk is that I will first introduce this type theory to you. I will show you how to do both cost-sensitive and functional reasoning, program reasoning in CAF. And I will define the cost-sensitive adequacy property. Next, I will integrate higher-order recursion in CAF by means of synthetic domain theory. I will define a cost-sensitive generalization of SDT and prove the cost-sensitive adequacy property in this new theory. In CAF, we can think about the cost structure of programs as an abstract effect f of a, which supports a operation called step. We can think about step of C as taking C abstract units of resource. For example, we may define a version of insertion sort in which we place steps in the body of the code to represent the usage of resources. Under the hood, we may define this abstract effect by using the rider monad on a cost monoid C. This evidently induces an equational theory on programs, which we may use to establish the cost bounds of algorithms. Given that we can speak about the cost of programs, how do we now speak about programs in terms of their pure functional properties? For example, we may assume that both insertion sort and merge sort satisfy the same logical or functional properties because they're both sorting algorithms. But in this setting, it's not automatic that insertion sort is equal to merge sort, precisely due to the fact that they have different cost structures. To see how CAF resolves this, we first observe what happens in the ordinary case of modeling cost. In particular, we have that the pure functional semantics of programs is naturally modeled in a category set. But this category is in some sense too flat. The cost effect, f of a corresponding to the rider monad, does not correctly distinguish data from cost structure. CAF resolves this by means of a new dimension or phase for representing cost. More precisely, we say that CAF is just the internal type theory of the category of families. A type in this category can be thought of as a cost-sensitive type denoted with A closed, equipped with a restriction action to its purely functional component. We can think about this as the Kripke or possible world semantics over the interval in which the open point lies below the closed point. In particular, presheaves over this interval exhibits a phase distinction between the functional phase and the class-sensitive phase of the CAF type. In the class-sensitive phase, we have that insertion sort and merge sort are different because they exhibit different cost structures. However, these cost structures are forgotten in the functional phase, thereby equating the two programs. This is well, you can think about this as the presheaf restriction action from the closed point into the open point as trivializing the cost structure. Now we can speak about this more precisely in terms of modal types that are either purely functional or purely cost sensitive. We say a type is purely functional or function modal when it comes from an actual set. In other words, it is the family defined by the identity map. We say a type is purely cost sensitive or cost modal when it's determined by the terminal map. Using this idea, we can then say that the abstract cost effect is defined by a cost modal monoid object C in the category of families. For example, we may take C to be the terminal map out of the natural numbers monoid. In this case, we may see that the restriction action of the presheaf quite literally just forgets about the cost component. To see how this aids us in reasoning about programs in CAF, we observe that modal types can be also defined in terms of the internal language. In particular, we'll use the intermediate proposition in the category of families as the as the proposition corresponding to the functional phase, in the sense that assuming this intermediate proposition can be thought of as restricting to the functional phase of CAF. In particular, we have that a type is function modal exactly when the function type out of this intermediate proposition or function phase proposition is equivalent to the type itself. And similarly, we say that we have that a type is cost modal when it is trivialized in the functional phase. So a function modal type thinks the functional phase holds, and a cost modal type thinks that the functional phase is false. Now, any function type from the function phase into the type is function modal. To construct a cost modal type out of a given type, we may use the following push-out diagram. The cost modality so induced can be thought of as quotienting the given type to a unique point in the functional phase, in which we have a proof of the intermediate proposition. Using this, we may define the abstract cost effect with a cost monoid that's in the image of the cost modality. We observe that insertion sort and merge sort are unequal because this monoid is not necessarily trivial. But on the other hand, by its very definition, it is trivialized in the functional phase. And therefore, in the functional phase, the cost of both insertion sort and merge sort disappears, and they're equal in their capacity as pure functions. Now we observe that cost analysis in CAF is purely equational or denotational. The questions I want to address in this talk is, how do we relate this equational style of reasoning to the operational cost semantics of actual programming languages? And the second question is, given that CAF is a type theory equipped with a theory of total functions, how do we reconcile this with the fact that programming languages have general recursive functions? The solution is to enrich CAF with a notion of partiality by means of synthetic domain theory. And it will relate programming languages and this denotational style of reasoning in CAF with an internal cost-sensitive version of the classic computational adequacy property of plugins. The upshot is we will be able to program with general recursive functions in CAF and also obtain a generalization of Plotkin's adequacy property. To take an example, we'll take the simply type lambda calculus equipped with a cost effect, f of a, just as before. Internally to CAF, we can think about the syntax of STLC as an inductive family given by a type, a type theory type U of object level types and a family of terms over this type. The internal denotational cost semantics, was there a question? Okay.
Oh.
Okay. The internal denotational cost semantics of STLC is given by a function that maps a STLC type to a real type and a family of functions that maps a term to the specified, an element of the specified interpretation of the type. Note that as before, we interpret this abstract cost effect by means of the Rider monad on a cost monoid. And similarly, the internal operational cost semantics is defined just as usual, except we take into account the cost of evaluation. We say that a language satisfies cost-sensitive computational adequacy when for all computations at base type, the denotational and operational cost semantics coincide. Thus, we can intuitively think of, in the classical case, that the denotational semantics carves out functions that are definable operationally. In this generalized setting, we can think about the image of the denotational model as carving out functions that are definable operationally in a cost-reflecting way. In prior work, we instantiated this schema with first-order recursion. And in this work, we would like to extend it to PCF with higher-order recursion. And to define the denotational cost semantics of PCF internal to a type theory, we need a notion of partial functions. The first attempt might be to, instead of modeling CAF in families of sets, we model in families of omega CPOs. But this does not yield a model of dependent type theory. Instead, we'll integrate recursion by means of synthetic domain theory, which can be thought of as an intuitionistic type theory equipped with a class of predomains in which all predomain maps are automatically continuous. Concretely, this is given by a topos equipped with a full subcategory of predomains. To start, we'll need an object called a dominance, whose elements can be thought of as the domains of definition of partial maps. And a dominance is just a collection of propositions closed under the true proposition and dependent sums. For the purposes of domain theory, we'll require that the dominance is also closed under the false proposition. As a side remark, the dominance also has the role as the classifier of Scott open subsets of predomains. Now, in a topos, a dominance induces a lifting structure defined in terms of a dependent sum type, in the sense that we can think about partial maps whose domains are classified by a sigma proposition as total maps into the lifted type. Lifting also induces an incidence relation that includes the initial lift algebra into the final lift coalgebra. We can think about this incidence relation as a figure shape that we can use to state the completeness properties of predomains. In particular, we have that every predomain has the unique extension property along this figure shape. Observe that this is strictly analogous to classic omega CPOs, which has the extension property along the figure shape in which the generic chain is included into the chain equipped with a top element. A model of synthetic domain theory now is given by a topos equipped with a dominance that is also a predomain. And every such model induces a full subcategory of predomains that has the following closure properties. It is closed under all limits and exponentials. This means that we may define the type structure of PCF. Moreover, all colimits exist, which we use to define the cost modality, which recall is defined by a pushout. And lastly, every endomap of domains has a fixed point. Therefore, we may interpret the fixed point operator of PCF. Now, just as a side remark, we often have that the dominance is strictly included between just the true and false proposition and the entire dominance, the entire class of propositions, which is needed to ensure that every map definable using every partial map whose support is classified by the dominance is actually continuous. To interpret PCF with this cost effect f of a, we need a proposition that represents the functional phase. We extend the basic model of SDT with a phase distinction. And the requirement is that this proposition is a sigma proposition. Now we may interpret the cost effect as just as before, except we will lift the interpretation with the lifting structure. Observe that we need this phase proposition to be a sigma proposition to actually define any types that are closed modal, that are cost modal, sorry. Now we need to define the operational cost semantics of PCF. A point that we need to take care of is that in the proof of computational adequacy, we need the fact that the operational cost semantics can be seen as a sigma proposition. To this end, we'll define this evaluation or operational semantics as an actual recursive function in CAF. And the idea is that we'll take the one-step transition relation, which here we call out, that takes a term and tells you whether it's terminated or has not terminated. And we'll repeat this one-step relation in terms of a recursive function. And we'll use the cost algebra map to accumulate the cost along the way. To prove computational adequacy, we define, as usual, we go by a logical relations argument between the syntax and semantics of PCF. Here we need to take care of the definition of the relation at the this computational this type that encodes the abstract cost effect. And the idea is that we'll quantify overall compatible closing contexts for closed terms of f of a. And the idea is that we will a denotation and a piece of syntax are related at this type when they're related for all compatible closing contexts. And a closing context in this case is just a continuation of the computation. In other words, a map from A to f of 1. And in the above, we write less than for the specialization order or the definedness order on f of 1, which is just a partial computation of a cost. This somewhat elaborate definition of the logical relation at the cost effect is needed to ensure that the subset defined as all the elements that participate in the relation always forms a sub-predomain. In other words, is always admissible, which is needed in the proof of the fundamental lemma of the logical relation. And speaking of the fundamental lemma, we have that we can prove this fundamental lemma, given that we use this definition for the logical relation at the cost effect type. And from this theorem, we have a very easy corollary, which is what we wanted to show from before, that at base type, the denotational cost semantics and operational cost semantics are the same. Now, to interpret this new cost-sensitive version of synthetic domain theory, we'll define a model that is fibered over the category of families. To start, we'll isolate a category of internal DCPOs in the category of families. Taking pre-sheaves, we almost have a model of synthetic domain theory, but to get an actual model, we need to preserve some colimits that are in the base category of domains. And this is done by restricting to sheaves for the extensive coverage on the base category of domains. We have that the category of sheaves on this site now furnishes a model of cost-sensitive synthetic domain theory, in which the phase proposition from the category of families is preserved by the Yoneda embedding. Now to wrap up, I'll discuss some related work. Our approach to doing internal computational adequacy is heavily inspired by prior work in this area, in particular by Simpson. And our model construction is builds on the model construction, the relative sheaf models of synthetic domain theory. And of course, this whole enterprise was started after considering the this type theory CAF that was used to unify both cost and functional reasoning for program verification. And in particular, this work extends our previous results from first order recursion to PCF. And lastly, our denotational cost semantics is inspired by prior work on effectful versions of PCF. To conclude, we've integrated higher order recursion into this CAF type theory for cost and functional reasoning. We proved an internal cost-sensitive adequacy theorem for PCF, which we use to connect denotational and operational reasoning for cost analysis and type theory. We substantiated our axiomatics by means of a relative sheaf model of the function cost phase distinction. For future work, we would like to generalize this result to recursive types and also look into how to relate our internal computational adequacy theorem to an external statement about PCF. And thank you for listening. I'll be happy to take any questions.
Okay, thank you very much. Are there any questions? Sure. I have a question. So if I understand correctly, the costs are only for terminating programs. Is that correct?
Yes.
Yeah. So is there any way of doing ones where you have like streams of costs for a non-terminating program, streams of text for a non-terminating program, so you can observe that they did something?
Yes, I haven't thought too much about it, but it seems reasonable. I think it's a little hard to think about like examples of I guess the canonical example would be streams. Yeah. Yeah, I'd have to think more about that, but that does seem reasonable. I'll just say that this theory is has been, well, it started out as being focused on analyzing cost bounds for inductive data types. So that's something that we looked really hard at, and my collaborators have looked into cost analysis for co-inductive data types, and so we've looked I know it's been done, but I don't know how to combine it with partiality. Yeah.
Okay, thank you. Any other questions? No, so thank you very much. So that's the end of the session.